you all for coming, especially on a cold evening. So I really appreciate everybody coming out. So today I'm going to talk about the intersection of physics and biology, probably with a little bit of a leaning towards physics because I was trained as a physicist. And the sort of the big theme that I want to talk to you about today is this idea that, let's see, this idea that so biological systems, as you all know, come in this enormous variety of shapes and sizes, from tiny, tiny little microorganisms to giant sequoias and everything in between. But despite this huge variety, this is not a free-for-all. There are constraints that the biological systems have to follow. So there are all of these systems, there are certain tasks they have to perform. So they have to eat, they have to breathe, sometimes they have to move, they have to swim. And all of those questions are fundamentally questions about transport, right? So transport of nutrients, transport of fluid, transport of the organism itself. And when you think about transport, the effectiveness or the efficiency of transport is governed by physical laws. So those physical laws are putting some constraints on the biological systems. That means in theory, that suggests that if we understand those physical laws and those physical constraints, that will help us to understand why we see different kinds of shapes and forms in these biological systems. All right, so that's the big idea of what I want to talk to you about today, and I'm going to give you three specific examples, and hopefully by the end of this, I will have convinced you that physics has played an important role in the evolution of some of these forms that we see in the biological systems. Okay. So the first system I'm going to talk to you about is bats. Okay, so bats our work. Oh, by the way, I should also say if anybody has questions in the middle, just interrupt me at any time. Throw your hand up or shout out. It's not a problem. Okay, so bats. So our work in bats, we got interested in bats because there was this amazing video that was posted by Sharon Schwartz's group from Brown University about bats drinking. And I have her video here. So this is the video that we saw that got us interested in bats. So this is a bat tongue. I don't know if you guys can see that. All right, so you looked at that. And so the hypothesis behind this is that this bat tongue, as you can see, it's got hairy structures all over it. And that these hairs have evolved to aid in the uptake of nectar. Okay, so the question we want to answer is, do the hairs help for uptake of nectar? And if so, how would you want to design those kinds of hairs? Okay, so in order to study this, the first thing we had to do is we had to make a hairy surface. And it turns out it's actually kind of hard to make a hairy surface. If you imagine how you might go about doing this. So this is the hairy surface we manufactured. This was done by one of my postdocs who was brilliant to make this work. So the reason this is hard to make is you can see there are all these fine structures. And so if you try to make a mold and then cast it, you break all of them when you try to pull things out of the mold. So he figured out sort of all the chemistry to actually manufacture these. So we were then able to make all of these hairy surfaces, and we could change the length of the hairs, the density of the hairs, the packing of the hairs, all of this, and actually do the experiment. So we made these fake bat tongues, and we looked at what does it look like when you dip these hairy surfaces into a bath of water and pull them out. So here's what it looks like. Let me show you. So I'm going to show you two videos. This thing up here, can you see my mouse? Yeah. So this thing up here is just the clamp that's holding the hairy surface. The hairy surface is down here in the bath. Similarly up here, this is the clamp, this is the hairy surface. This one has sparse hairs and this one has dense hairs. And I'm not going to pull both of these out of the bath. All right. So here's sparse hairs being pulled out of a bath. Okay, and if you look closely, you can already see what might be a problem if you're a bat and you're trying to get this fluid into your mouth. Here's the dense hairs, which does a little bit better, but you can see there's also a problem with that one. So now if you are a bat and you are trying to get as much nectar into your mouth as possible, let's think about what the problems are with these two extremes that I've shown you. So on the sparse hair side, this is some frame from the film. You can see a lot of that fluid has drained out, right? So these are empty hairs up here, and this is the fluid down here. So a lot of it has drained down.
Did you use just water, or did you change the
This
viscosity?
this is a little bit more viscous than water. Yeah. So this was pseudo nectar, maybe even a little bit more viscous than nectar, since these are bigger than bat tongues. Yeah. Great. Yeah, good question. By the way, we're going to talk about viscosity a lot coming up, so I appreciate that question. Okay, so on this one, on the sparse hairs, you can see a lot of the fluid has drained away, and so the problem is fast drainage on this one, that this fluid is not going to make it into the bat's mouth, which is up here somewhere. On the dense hairs, you do better in keeping the fluid, but the problem is that all of this space is now taken up by hairs instead of delicious nectar, right? And so you would like that space to be taken up by nectar instead of hairs. So on this side, you are constrained because you've reduced the volume for the nectar because of the hairs. And on this side, you're constrained because things are draining way too fast because you don't have enough hairs to hold it to the tongue, which means that we now have an optimization problem. And as a physicist, I love an optimization problem. So an optimization problem means that there's a trade-off between these two things where the bat is going to maximize the amount of fluid that it pulls into its mouth. Okay? Okay, so both of these things are things that we can compute. I'm not going to compute them in front of you because I don't want you to have to watch me do math, but I will show you the answer, okay? And I will tell you that on this side, well, I'll just show you the answer. So this is the answer. And I'm going to now write this in words, what the answer is. This quantity over here is the amount of fluid that goes into the bat's mouth. Okay, and the amount of fluid that's going into the bat's mouth depends on how much volume am I losing because of the volume occupied by the hairs, and that's just a geometry problem. So that's just a geometry problem where I'm asking, okay, how much volume is taken up by these circles? Okay, and how much am I losing because I lost it to drainage? And this is just a fluid mechanics problem. So for those of you who think about drainage and fluid mechanics, this is something that we teach in the first semester, and so that's something you can compute. Okay, so now, all right, now we have something interesting to think about here. So if I think about this from the point of view of the bat, and the bat is evolving in some way, or the bat over millions of years is evolving to pick something about the structure of these hairs to pick up as much fluid as it can, what are the things in this expression that it can change? So there are some things in here that I've hidden in here, which I haven't talked about, like gravity. Okay, the bat can't change gravity. The viscosity of water, it can't change the viscosity of water. The things that it can change are the radius of the hair and the spacing of the hair, right? So over time, these hairs are the hairs are gonna sort of, in evolution, you're sampling a bunch of this space. So the bats can try a bunch of different size hairs and a bunch of different spacings. And if one of these things gives you an evolutionary advantage, then those are more likely to be propagated along. Okay, so I have an expression now which says the amount of fluid that goes to the mouth depends on the radius of the hair, which is E, and the spacing of the hair in some way. I know what that way is. And I'm now going to plot for you this map, the amount of fluid that goes into the mouth as a function of those two things. Yes?
Is the length of the hair important?
Oh, great question. The length of the hair. The length of the hair has been scaled out. And the reason it's been scaled out is, that's a great question, is this is actually a non-dimensionalized version of the amount of fluid that's going in. So the length of the hair came in on both sides and canceled. That's a tricky question.
What about the diameter of the hair?
Diameter hair is there. The diameter hair is in E. Right there. Yeah, it's good. So E matters, diameter and spacing matters.
Stiffness of the hair.
Stiffness, good question. Stiffness, we're assuming no bending. We're going to do bending later. But right now, we're going to assume no bending.
Yeah. What about the surface of the hair?
Oh, the surface of there. Yes, so the surface, we assume it's wetting. In the experiments we did, it's wetting. In the bat, it looks wetting. So we think it's probably okay. But actually, that's going to come up later when we get to otters. So hold that question.
Is it also curvature of the hair?
The curvature. Oh, yes. So for this calculation, we're looking at straight hairs. The curvature actually could matter because so right now we sort of took the simplest case and just looked at, if I think about volume, the volume is sort of gonna be the same whether they're like this or they're like this, since they're the same volume. For the drainage, if they lie all the way flat, then it's gonna be a problem. If they only curve a little bit, the drainage calculation is probably okay. Oh, yeah. So if they do something like this, if you're draining this way, it does matter. It matters a little bit, but I'll show you the calculation and we'll see if I can convince you that I can neglect the curvature. That's good. It's good. Yeah.
The hairs themselves like cylindrical or are they conical?
Oh, yeah. Right. So in the real bat, they are conical. In this model, they are. Oh yeah. So what I've shown you here, just this very simple calculation is cylindrical. When I compare it to the bat data, we actually put in a conical shape that matches the bat. Yeah. But to get the concept here, I put cylinders. Great. Yeah.
What about the material itself? Is it hydrophobic, hydrophobic,
Yeah.
that sort of thing?
Yeah. So this was related to this question over here about the material. So in our experiments, we had the fluid we used was silicon oil, which wets everything. So in our thing, everything is wetting. Presumably the bat is also wetting. Although we don't have a bat tongue, so I haven't been able to test that. If you hold that thought, I'll show you some evidence when we look at otters that it's probably not the dominant factor in this. Right. It's a great audience. That's okay. Fantastic. All right, so I'm now going to show you this is the amount of fluid that goes in the mouth as a function of E and R. Okay, so I'm just plotting this function. So if I just plot this function, it looks like this. So this is M. Each one of these colors is for a different R, and this is the hair diameter. Okay, so again, I just plotted that function. And the fantastic thing about this plot is that for every one of these curves, there's a maximum, right? Which means there's something for the bat to pick, right? So for example, I'll just put the max, I put dots over here like this. So if I look at this lowest purple curve, this R is equal to 0.6, if my spacing is this, the bat would like to pick an E of about here, right, in order to maximize the fluid uptake, right? And as my spacing gets smaller, it's going to move E this way to get it smaller and smaller, okay? If this is the thing that it's trying to do is to maximize fluid uptake. So the next thing I'm going to show you on the next slide is I'm now going to take this plot and I'm going to say, so this plot is basically telling me for every E, there's a preferred R. For every hair radius, there's a preferred spacing if I want to maximize the amount of delicious nectar that this bat is going to take up. Okay?
Why doesn't the bat just use the straw?
Yeah, it should do that. That would be better. By the way, I think hummingbirds actually have a straw. They have a tongue that the surface tension will run the straw. But yeah.
What about the temperature and what are the
Yeah.
conditions of the fluid?
Yeah, so viscosity is sensitive to temperature. It's very sensitive to temperature. In this calculation, the changing the viscosity changes the scale. Oh, actually, the viscosity could change the scale on that. So I'll tell you what we did again when we compared it to when we get to the real bats. So in the literature, this is the other thing that I've learned doing these questions about biological projects. Biologists have measured everything. It's incredible. Like anything you need to find, you can find that they have measured it. So we looked at the viscosity of the nectars from the different flowers that the bats were drinking under the normal drinking conditions, right? Because presumably they measure them in temperatures where the nectar is typically existing. So there's certainly going to be variation in that. But the numbers that I'll show you were based on measurements that were made in the field. Yeah.
So your measurements are made against the gravity. The bats hang upside down, so.
Oh, yeah, yes. So, but when they drink, actually, I should have a picture of the bat drinking. When they drink, the flower is here, and they do this, and then their tongue comes in like this. Yeah. So I think, yeah, and actually that's true. If they could fly upside down and drink this way, that would probably help. But I've never seen a bat do that.
They just have to slurp.
Yeah, exactly. Yeah.
Well,
Yeah.
looking at that graph,
Yeah.
it seems the optimum is
Yeah.
R equals 0.01
Yeah,
and E equals 0.05.
yeah.
That means there's practically no space left between the hairs.
Yeah, exactly, correct. It's even worse, actually. This is a very good observation you have, because in fact, I just stopped this at R equals 0.01, but if I kept going smaller and smaller and smaller, it would keep going that way. And the limit, so not only is the limit that there's no space between the hairs, it's the limit that the size of the hair goes to 0. Right, so now we're in a very strange limit where my radius of my hair becomes nothing. And the radius of the hair becomes nothing. That is exactly what you would want, in the sense that you want something where the volume is not taken up by any of the hairs, but it is resisting the drainage. Right, so there is a singular limit where everything goes to 0. So I think the way to think about this problem is that the bat, there are I can't make a hair that has radius of 0. There's no physical mechanism for me to do that. Yeah. Yeah, right. So if there's no physical mechanism, that means there's some physical structure that the bat is using to make that hair, which sets the radius, which says, okay, that's the radius at which my hairs are not going to break off. There's other limits here that the strength of the material is going to withstand this sort of dipping action. And then once I have that hair diameter, now I'm going to pick the spacing that's appropriate for that hair diameter. But you're absolutely right. If they could actually make a hair that has 0 radius, that's what the system would be driven to.
And it will also be 0 space.
And 0 spacing. That's right. 0, exactly. Yeah. So it's a strange singular limit. Yeah. Yeah. Good. Yeah.
Surface tension, what about surface tension?
Yes. Surface tension. Okay, so first, surface tension is my favorite thing. All of my initial papers were on surface tension. And I will, so I don't have the picture here for the bats. I'm going to tell you to hold that question for the otters, because I have evidence that surface tension, much to my dismay, is not playing a role in the system. Yeah. Right? Okay, amazing. All right, so now I'm going to plot for you the optimal E versus R, which is going to show exactly what you said, that in the limit, both of these things are going to go to 0. So here's the ratio of E versus R that maximizes the amount of fluid uptake I have. Okay, so this is if I have a hair diameter of 1.5. This is all non-dimensionalized. So of a non-dimensional 1.5, then you can read up there what the hair spacing should be to maximize the fluid uptake. Okay. And, oh, you can't really see. There's a gray band on here, which shows you sort of when you're within 99% of that line, but that's not terribly important. Okay, so if those hairs on the bat have evolved to maximize the amount of fluid uptake, then I should be able to measure them. So I can go to that video. Here's the video. I should be able to measure the spacing and the thickness of those hairs. And if this has been evolved to maximize the uptake of fluid, it should sit somewhere on that line. Yeah. Okay. All right. So here's what you do. So we measure the bats and they sit right there. Amazing. We were so excited to see that. I mean, biology is so messy. To get something that close is incredible. So, okay. So we got the bats. Then so I gave a talk on this, and I got a call from one of my colleagues, Alejandro Rico Guevara, and he said, you know what? I have an animal that has a hairy tongue too. It's the rainbow lorikeet. I said, well, send me the rainbow lorikeet spacing and hair diameter. And he did. And here's the rainbow lorikeet. Amazing. Then I learned, oh, wait, there's another one. There's the honey possum has a hairy tongue. So it's right there. It's incredible. So, so the other thing I learned doing this, and I didn't realize this actually until I gave this a piece of this talk a couple of weeks ago. I mean, these are all Australian animals. So there's something about Australia where animals have hairy tongues. So, I'm about to move on to my next animal, but I'm going to say, if anybody knows of other Australian animals with hairy tongues, please tell me. Okay, great. Can you measure the spacing and the thickness? Because I think there are other ones that we can put on this chart. Cats' tongues are sandpapery, so it's not hair. It's rough, but it's not a hair. Yeah.
Cats
Yeah.
drink water exclusively
Yes.
with surface tension.
Yes, yes. So cats, so there's a very good art, you might be referring to this. There's a very good article in Nature on cat drinking. Yeah, I'll tell you, actually, I will tell you an aside on the cat drinking article. So the cat drinking was done by one of my colleagues, Roman Stalker and Pindro Rice. It's a very nice article in Nature about cat drinking. And this came about because Roman had a cat. And so he was watching his cat drink and he was filming it with his iPhone. And so they did this study. They noticed they're doing this really interesting thing with lapping, and they did the fluid mechanics study, and then they wrote the paper. And once they sent the paper in, they realized they had not gone through all of the paperwork to do the animal study, right? Because you have to do the animal study. So the animal study experts called me and said, they should have done the paperwork first, but we're trying to do an exception. And we need you to write a letter saying that Roman's cat was not harmed by filming the drinking. So you're welcome. Anyway, yeah.
The question came up about being upside down when drinking.
Yes. Yeah.
Do you know which side that would put you on this curve? If you were upside down, would you be above that curve? More likely?
Oh.
Because I frequently see rainbow lorikeets.
Lorikeets upside down. Oh,
I'm
that's.
frequently holding on, and yeah.
Yeah. Okay. So if I go upside down, that changes the sign on the drainage.
I would tend to think you would want bigger spacing.
I think that's, yeah. So you want the bigger spacing. Yeah, I think that's right. Oh, that's good. Oh, so maybe we need to put in like the average angle at which they're drinking, and then that moves that'll move the lorikeet point down. Good one. Right.
It's like changing the gene.
Yeah, exactly. Yeah.
And also that when they're drinking from nectar from a flower,
Yeah.
the wind, because it can blow.
Yes. Yeah, exactly. Yeah. And there's a whole other set of beautiful experiments. This was done by a group in University of Washington about the control that is required to drink from a flower in the wind to follow. I mean, it's a really interesting control problem. They've done beautiful studies on that as well, moving the flower and see how actually they did it with a moth to see how the moth adjusts in order to continue drinking as the flower's moving. Okay, great. It's great. Okay, excellent. All right, so that was my story about bats. So I'm now going to move on to the next part of my story, which is going to be how to swim if you are very tiny. Okay, you can't see that, but anyway, so how to swim if you're very tiny. So the thing about swimming when you're very tiny is that the physics of fluid mechanics is very different if you are very small than when you're very large. Because if you are very small, you are dominated by viscous effects, right? So viscous effects are things that oppose flow, which is why, so if you think about honey, it's a very viscous fluid, so it doesn't flow as easily as water flows. Okay. And when viscous effects are dominant, very strange things can happen. So this is a famous demonstration I'm going to show you. This is a demonstration done by a guy called G.I. Taylor. So G.I. Taylor is one of the giants in fluid mechanics. And he's going to show just sort of a classical demonstration of what can happen in viscous fluids. So this is something that's called a Couette cell. And a Couette cell, it's two concentric cylinders. And you spin either the inner or the outer or both. And you put a fluid in the gap and you see what happens in the gap. Okay. So this is his Couette cell that he's built over here. He's going to spin the inner one. I'm going to show the movie. This is actually G.I. Taylor doing this. You'll see his hand in a minute. And he's putting now a drop of dye in the fluid that's in this gap between the two cylinders. Okay, so you can see what happens when he starts to spin this. All right. So there's G.I. Taylor's finger, and he's now going to mix that drop of dye in. So he's just turning the inner cylinder. That's the only thing that's happening. So he's turning the inner cylinder. He's going to do this a few times. I think maybe 3 or 4 turns, maybe 4. So it's going to come around like this. And now he's just going to go the other way. So he's now mixing in the other direction. So you can see that drop has been nicely sort of mixed into the fluid. You can barely see it right now because it's kind of blurred away. So now he's gone back to, He's going to go back one more, and now he's going to come back to on the fourth turn around, and he has now unmixed the drop. Did I just blow your mind? Okay, and that was real. That was not playing the video backwards. This is actually what happens at low Reynolds number. And low Reynolds number is a system where viscosity dominates. Okay, and viscosity dominates. That means there is something that is called kinematic reversibility. Okay, and kinematic reversibility says that if I force the fluid in one direction and then I exactly back up what I just did, you get back to exactly where you started. And this is a problem if you're trying to swim, if you're very tiny. Because if you're tiny and you're dominated by viscous forces, if I do something like this, I go this way, I have to go back to where I started, and now I'm literally back to where I started, right? So you have to somehow break this kinematic reversibility if you're very tiny and you want to move somewhere, okay? And so that is why tiny swimmers are shaped like this and big swimmers are shaped like this. They're shaped very differently, right? So big swimmers, they care about things like being very aerodynamic or something, I guess, hydrodynamic, right? So to get a nice airfoil kind of a shape. And tiny swimmers don't care anything about that. They care about breaking that kinematic reversibility, right? So what is the trick you can do to break the kinematic reversibility? Okay, so there's been a lot of great work on tiny swimmers. This is one of my favorite papers on this. This is by another giant in fluid mechanics, James Lighthill, who wrote a Cyan review in 1976 on flagellar hydrodynamics. I'm going to tell you what the flagella is in a minute. But in this paper, he has one of my favorite figures. And this, I'm going to put the figure up in a minute. This is a fluid dynamicist's view of biology. So when a fluid dynamicist is trying to figure out what is going on in a biological system, this is what it looks to someone like James Lighthill. It's a mess. It's very hard to sort out. Okay, so this is biology. And actually, I should say the other thing I love about this is this was clearly done in the days before PowerPoint when you had to draw everything by hand. It's fantastic. So, but the great thing about this is that Lighthill has organized these organisms by how they swim. Okay, so which is what a fluid dynamicist would do. So, so everything in this pink circle here basically looks something like this. There's kind of a head, which is kind of round-ish. Not all of it is round, but they're round-ish. And some number of tails. In this circle, it's usually one or two, right? And they're all doing something along those lines to propel this organism forward. The other boundary you see in here is this boundary here, which I just marked by green. And this is the boundary between the prokaryotic cells and eukaryotic cells, which to first order, I know there's biologists in the room who know much more about this than I do, but first order, the prokaryotic cells you can remember from high school are basically bacteria, and the eukaryotic cells are basically everything else, with probably many exceptions, but roughly we can think about it that way. And we are going to be interested today in the eukaryotic cells, which sit here. Okay. Oh, I don't know if you can see that, but it's basically in the sort of the bulk of this pink area over here. Okay, so there is something very interesting about eukaryotic cells with flagella. So this is my one slide on eukaryotic cells with flagella. So, so in this case, I'm just going to draw it with a head and one tail. And if I zoom in on that tail, the tail is called the flagella. The cilia also have this structure. They have something that's called a 9+2 microtubule structure. Okay, and the 9+2 microtubule structure looks like this. So if I zoom in on that little segment, there are all these little microtubules which can slide relative to one another, and that sliding allows you to create a bending moment. So you can change the shape of the thing, which is how you swim, right? So that's how changing the shape of the tail. If I slice through that cross section, the slice to the cross section looks like this, or this is an actual picture, and it always looks like this. So it always has 9 pairs of microtubules around the outside, and then 2 in the middle, which is why it's the 9+2 microtubule structure. And it's always 9+2. It is not 10+3. It is not 7+4. It is always 9+2. And it is always 9+2 across all species, right? So this is what it is in algae. This is what it is in the cilia in our lungs. This is what it is in the sperm of rhinoceros, of anything. It's always 9 + 2. Okay, and that means that the diameter of that tail is approximately the same for all species, which will be important in a minute in our calculation. Okay, so that's one remarkable thing about the tails in eukaryotic organisms. The other thing is that because they have these sort of sliding microtubules, they can apply these, they're basically a little engine, right? So they have little motors along here, so you can change the shape of this tail. So the first thing you might ask is, what shape should you select if you're going to be a good swimmer, right? So that's one thing they can pick. And we can do that calculation. I'll just show you what the answer is. I'm going to get to the morphology question in a minute. But you could say, okay, so let's take the simplest geometry. I'm going to have a roundish head, and I'm going to have some tail of length L. That's going to be the geometry. And I'm going to say, okay, what do I mean by a good swimmer? Well, let's take a very simple organism. Let's take sperm, because we know that they have a very well-defined objective function, right? Sperm have their objective. They have a packet of genetic material, and they have to move it from one place to another. That's it, right? That's my objective. I have a payload, and I have to move it. I don't have to eat. I don't have to do there's all this stuff. I have a payload. I have to move it. So if my objective is to move this payload of genetic material, what shape should I pick for my tail? And again, that's just a fluid mechanics question, right? So I can, those are all physical questions. So I can just do that, and you get this. So this is the swimming dynamics you get. And there are many fantastic biologists who have measured this, and you can check that the computed, if you optimize this thing for swimming, the computed wavelength and periods match what's measured in the literature. Okay, so it's pretty good. All right, but my objective in this talk is to talk about morphology, right? So I want to know if I am now evolving this thing, and my objective is to carry this payload. I have a packet of genetic material. For a given size payload, how long should the tail be? Okay, that's the question I want to ask. All right, and you could imagine, just like before, I could put in a short tail, or I could put on a long tail. The short tail, you're looking at that and you're like, okay, that short tail doesn't look very good, right? There's not enough power or propulsion on that, right? So if you go too short, that's probably not going to be great. There's also a problem with the long tail, right? And the problem with the long tail is that you get high drag on that tail. And so you're spending all of your energy moving the tail instead of moving the payload, right? I could make this tail infinitely long, but then I'm putting in a huge amount of energy to move a tiny little payloads, right? So that tells me, okay, there's probably something in between, which is again an optimum, right? And again, you're seeing the theme that's coming out of this talk, that there are these trade-offs which we can calculate mathematically, which give us these optimal structures. Okay, so I can do this calculation. Again, this is just a straightforward fluid mechanics calculation. I have a sphere and something doing this, and I can do that calculation. So we do that. And yes, there is an optimum. So this is now the answer. So let me walk you through this plot. So this axis here is the ratio of the tail length to the head size. Okay? And this axis here, you can think about this either as swimming efficiency or swimming speed. For these viscously dominated systems, they're equivalent. Okay? And you can see that there is a best point for swimming. Okay, so if I look over here, so these are my short-tailed swimmers, right? So L/R is very small, so that's a short tail. That's a long tail, and that's a medium-sized tail. And you can see the medium-sized tail again wins, right? Because my swimming efficiency is really good. Okay, and the great thing is I can now take that. So that's my optimal. I can just go down here and say, oh, what is the ratio that optimizes the system? Oh, it's 12. Like the answer is 12. I've never done a problem like this where you go through, there's all these biological calculations, you have complications, you have to understand the structure of the tail, you have to make this model, you have to figure out what this is, and then at the end of the day, the answer is 12. That's it. Like there's no, oh, but it's for if they're swimming in this or it's swimming in this. No, the answer is 12. If I look at any microorganism whose objective is to swim efficiently, the ratio of the head to the tail size should be 12. That's it. period.
42.
Exactly, it's not 42, it's 12. Okay, all right, so now we can check. I mean, 12, again, this to me is remarkable. 12 is a very specific answer. So, my student Daniel Tam, who did this work, he went through biological literature, and again, this has all been measured. He looked at 400 species, so sperm of 400 species, and put it on here. And I'm not going to give you, I'm going to show you the histogram of the ratio of the head to tail size of 400 species of sperm that he collected. It's 12. It's 12. It's incredible. Okay, so these are picking something that is optimizing transport of that payload. But the thing so first, I love that the answer is 12. This is the only time in my life I'm ever going to get an answer that simple. But the other thing that I really liked about this problem is, so Daniel found this, he collected all this data, it was amazing. And I would go and I would give this talk in physics departments. Physicists would look at this and say, this is amazing. You found something universal. The answer is 12. It's very simple. It all comes out beautifully. And then I would go and I would give this talk in biology departments. And the biologists would say, yeah, this is a little bit interesting. But the more interesting thing are these guys over here. Right? Because these have been subject to some other evolutionary pressures to be put them out way so far off of that 12. Right. And so I think, this took me a long time to see the pattern as I was going between sort of biology and physics departments. And I realized, oh, you know what? Physicists become famous by making everything look the same. Right? That's right. It's just you want some universal theory that combines everything. You want the unified theory. Whereas biologists become famous by finding something different. And you get to name it after you or after some famous person. Right. So there's a whole, I realized that this reaction I was getting is there's something that is culturally different about those two different fields. Right. And so I kind of feel, if you are a person who likes taking things that are very different and figuring out why they're similar, you have a little bit of physicist in you. If you're a person who likes looking at a pile of stuff and figuring out why that one is unique, you have a little bit of biology. It's biologist in you. So you think about which side of that you like. But so the biologist pointed out, well, these are the interesting ones. So I thought, well, okay, if those are the interesting ones, we should look at the interesting ones. So the interesting ones, those guys are bandicoots, another Australian animal. Exactly, it's incredible. Okay, so bandicoots. I did in fact find that picture from scarysquirrel.org. Okay, so the question is, why are the bandicoots out there? Okay, so I don't know why they evolved to be this way, but I do know why they are not at 12. So bandicoots. So I told you a minute ago that the structure of the flagella is the same for all organisms. All species have this 9+2 microtubule structure, and they're all the same diameter. And I should have said it is the same for all species except bandicoots. And bandicoots, they still have the 9+2 microtubule structure, but it is encased in a sheath. Okay, and you can see the sheath is actually quite large. Like it makes this maybe an order of magnitude larger. The rate is an order of magnitude larger than what we had before. And in fact, all of the organisms that are on that tail have some kind of a sheath. There's a bandicoot and there's a Chinese rat, I think, that's in there. And because you have this sheath, that means that the bending stiffness of the tail has changed dramatically. And I did not take into account the bending stiffness. So if you put bending stiffness, it does push the optimal to the other side of in this direction on that chart. And again, the reason we know this is because there is this wonderful paper, the Bandicoot Spermatozoa and Electron Microscope Study of the Tail, that was done in 1958. Again, back to my claim that biologists have measured everything. If you have not found it in the literature, you have not looked hard enough. So so I think we now understand that as well. And like I said, I don't know why those particular organisms evolved the sheath, but I do know that everything out here has that structure, which is what's pushing them to this end of the side of the plot. Yeah. Oh, yeah. You first and then. Yeah.
Well, as I understood it, well, I remember, flagella don't they rotate.
Oh, yeah. So okay, there's two kinds of flagella. So there is, on the eukaryotic flagella, they are spirals like a corkscrew, and they rotate. And rotate and spiral, that's how they break that kinematic reversibility problem, because there's chirality. And if you have chirality, then you can tell if you're going forwards or backwards. But for the eukaryotic ones, they actually do primarily a plane wave structure. There is a little bit of rotation within that plane wave, but the beating is primarily in plane, and that's the difference between the prokaryotic flagellum.
Whenever they break the kinematic reversibility.
Yeah, so the kinematic reversibility, yeah, great question. So the way you have to break the kinematic reversibility is, so here's the way I think about it is, if I took a movie of this thing's motion and I played it backwards, would I be able to tell if it was going forwards or backwards? Right? So if I do this and you videotape me, you can't tell if I'm going forwards or backwards. If I do this, you can't tell if I'm going forwards or backwards. If I do this, you can tell because I have a wave and there's a direction. And so if I play it backwards, the wave goes in the other direction. Right? So the way you break the kinematic reversibility is you put a wave through the system. Yeah. Good. Yeah.
Alright, so the ones out at 25 to 30,
Yeah.
the efficiency is not far off.
Yeah.
What about the ones at 6?
Oh, yeah. Oh, great. Yes, the ones that say, yes. Okay, terrific question. Yeah, so you pack two very important things into this question. The one is that peak is actually pretty flat, right? And a lot of times in these biological systems, you do find these sort of flat kind of optima, which means that it's very forgiving around that spot, right? If I'm off by a little bit, I don't lose that much efficiency. And over here, okay, maybe I haven't lost that much by being out here. The question is, I've got this little yellow spike here where I have lost a lot of efficiency. Okay, so I'm going to tell you the first part of that answer is I don't know, but let me tell you what I do know about the yellow points. So those yellow points are something called even-toed ungulates, and the even-toed ungulates are things like cows, goats, sheep. They tend to be things that are domesticated. Right, and so I don't know if that's something that would actually put different kinds of evolutionary pressures on how you're going to be successful in reproducing. But I do know that that this little peak here comes from animals that have been domesticated for many years. That's what yeah. Great. Yeah.
You know what drives the 9+2 structure?
Oh, yeah, I wish, this is my favorite problem, and I do not know. I have not, there's been some speculation in the literature, but I don't think anybody has really picked out why that is. Yeah, I mean, that would be a phenomenal question to answer. Yeah.
On that, I don't have an answer for
Yeah,
that question,
yeah.
but there are mutations of ciliopathies.
Yeah.
Which change and clearly not as efficient.
It's efficient, yeah.
There's
There's something in there that I mean, in looking at all of these different systems, that is one of the most robust sort of structures that I've seen. But I mean, it is really replicated over and over again. So I think there is something behind it, and I don't know what it is. Yeah.
You've got when a sperm's evolving, or when the driving forces on it.
Yeah.
It's twofold. One is the male bit, the other is the female.
Yeah.
And presumably, if you've got a convoluted female trap,
Yeah.
you need more driving force on the male bit. So how does that fit into your model there?
Oh, yeah. Terrific question. So there's two pieces to this. So one is the sperm is not, like you said, it's not swimming in this nice free ocean. It's going through something that's very convoluted, and it's not even in a Newtonian fluid. It's in a fluid that has some elasticity, which also impacts the optimal swimming strategy. So I would say, I think you actually would have to do the calculation in a confined geometry with the real elasticity in the fluid. And people have done that, but not in an optimal sense. So people have done the simulation where I say, okay, I'm gonna take something with a head, I'm gonna put it in something that's got, maybe a wavy confined geometry like this with some elasticity. And you can see that the optimal stroke does change a little bit. It doesn't change dramatically, but it does change. And I would also say, I think that's an argument for not going on the end where the tail is too long, right? Because I think if you're going around sort of these tight corners, then you could get in trouble with a longer tail. But I think, yeah, and I think actually, I mean, I guess, I don't know, does anybody know if even-toed ungulates have a different female reproductive system? Maybe that's why they're off, that's a good question.
Yeah, well, I don't know, we used to do RA on chooks.
Yeah.
And they've actually got an assisting process, actually, as you drop the sperm onto the cloaca,
Yes.
the hen helps it go in, so it's not just simply the sperm swimming in, it gets an assistance from, so in evolutionary terms.
Yeah.
You've got these two
Yeah,
processes working together.
yeah. And I will say, I mean, there is a spread in this, right? So it's not, there's a very strong peak at 12, but there's certainly room for other things happening in the width of that peak beyond just the band groups. So yeah.
Does AI, does freezing affect the efficacy?
Oh, so I don't think we have data on that.
You say get data on everything.
That means I didn't look hard enough. Yeah.
So the short-tailed duck.
Yeah.
So what's the comparison made between, say, wild buffaloes and domesticated buffaloes?
Oh, yeah, that I would love to see that data. So I have not found that data yet. That data I bet is available, and I think that would really be really interesting to look at if you have a similar species or species that were converged fairly recently, and then look at the difference between the wild and the domestic. Because I mean, I think that's what you would have to do to know, is that peak coming from domestication or is it coming from something else?
Yeah, dogs and these days.
Yeah.
I'm just wondering, because wild pigs revert very quickly to getting tusks over a generation or two if you release them into the wild.
Ah.
Yeah, I'm just wondering, would you look at a sort of a generational shift, a study?
Oh.
I mean, if their physical appearance can change so radically, that maybe the tail might as well.
That would be, I would be super interested to see that data as well. I'm amazed that the physical appearance can change that quickly. That's, I mean, yeah, so if they really can adapt on such a short time scale, I would be, because I mean, I would also say, the evolutionary pressures on sperm must be so concentrated that if you are seeing those changes somewhere else, it wouldn't surprise me if you saw them.
Have you looked at the volume of sperm? Because with domesticated animals and breeding, they're going to look for effectively large balls and big sperm production.
Yeah.
And I don't know, maybe there's some effect where it's like having a school of fish.
Yeah.
And the volume of sperm actually helps them work cooperatively to move through. But with selective breeding, that would change. I think it would change because people are looking for high fertility, which is high volume sperm.
Exactly. Exactly. So first, I think there have been studies about swimming in groups. And low intervals number, again, it doesn't matter as much as a high intervals number, but I think your point is exactly right, that we are, when we are breeding these animals, if we're selecting for a high volume of sperm, that means we are not selecting for a ratio of 12. We're selecting for something else, right? And so that could certainly push this to one or the other side of the chart. So that would be my best guess at what's happening, is that when you domesticate, you're selecting for something else. But I don't know. Yeah, great. Yeah.
Why only one?
Why what?
Why only one tail? When you
Oh, yeah.
Swimmers with two arms generally go better than swimmers with one arm.
Yeah. So I will say, I mean, so there are plenty of swimmers with two arms. So I don't know why sperm happen to have one, but like Chlamydomonas is a very famous one. But Chlamydomonas, so we did a study on Chlamydomonas, which has two flagella, and they have two kinds of strokes. So one is where they have their two arms together and they basically move it like one, like this. And they have one where they do this, like a breaststroke, with their two little flagella. And this one is still the most efficient swimming, right? So if the only thing you want to do is swim efficiently, you basically do the same thing as you do with one arm. This is better for feeding. So if you're trying to stir stuff around and get as many nutrients to you as possible, then you need the two arms. So it could be that because this is sort of the most efficient for swimming, if all you have to do is swim, then you might as well just have one. If you're feeding, then you want to do this as well. Here was one. Yeah.
Is there any relationship about how far they've got to swim? So
Oh.
has there been any sort of evolution?
Yeah.
The long distance marathon runners compared
Yeah.
of sperm compared to the ones who've got a short.
The sprinters. Yeah. So another great question. So it turns out low Reynolds number saves you on this. That because of this, there are some implications for that kinematic reversibility, and one is that optimizing for efficiency at a particular speed is equivalent to optimizing for speed for a particular amount of energy that you have, right? And it's because that time comes out of the equations that those two are equivalent. So from the point of view of sperm, being a marathon runner or being a sprinter is the same thing. It just depends on when you lay out the energy. Yeah.
Yeah, I'm just curious what the data looks like if you remove the rodents from your graph.
Oh.
Like it looks, perhaps it's just a contrast, but it looks like you've shown that 12 for rodents, not necessarily.
Yeah, actually, yeah, it's hard. Yeah, so I'm not entirely sure. Yeah, it's hard to see in this plot. Let me look at my screen. So if you take out the rodents,
Yeah, I guess I'd be curious on it, the kingdom.
yeah, totally. So I think you're absolutely right. So the rodents, if I look at this, and you can come up afterwards and look, it looks like they are still peaked at 12, but they're broader. Oh, I see what you're saying. But you're saying like if I just looked at like the light blue ones, right? Yeah. Then you would have something that's much flatter. Yeah, exactly. Yeah. Yeah, and so I think one of the challenges is that there's like 4 dark blues in there. Yeah, it's a great question. And I think part of that is also just how much data we have in each bin. But after, you're welcome to come up and take a look afterwards. Yeah. But I do see what you mean by there's some where we don't have a whole lot of species, in which case it kind of looks pretty flat. Yeah. Yeah. Great. Okay, I have one more story. Do I have time to do one more story? Is that okay? Okay, I'll do one more story. This one's actually a shorter one. Okay, so the last story is about staying warm in water. Okay, so staying warm in particular in ice water. I'm again going to start with a classic paper. This is a paper that was written in 1950 by Scholander, who says, in man, even a few minutes of partial or total immersion in ice water causes unbearable chill and pain. And yet some Arctic mammals spend all of parts of their lives swimming about in icy sub-zero waters. Okay, and yet this, again, wonderful plot in here, where this axis is sort of the effectiveness of their insulation, however they're insulating themselves, and this axis is the thickness, so the thickness of fur or something. Okay, and over here you can see these open circles are the insulation in water, and then the filled circles are the same animals on land. Okay, so the way animals in water, mammals in water maintain their temperature, they have 2 strategies. So the first one is blubber. So you just have a thick thing of something that's insulating, right? And so that's, walruses do this, and there's many animals that do this. The other strategy is to use fur. Okay, and if you use fur, it is not the fur that is giving you the insulation. It's the fact that the fur can trap in a layer of air, and air is very insulating, right? So this is, I mean, why we have double pane windows is you put a gas in between them so that the thermal conductivity is very low, right? So So if you are using fur, you want to be able to trap this layer of air. And again, there are wonderful papers on this that have measured what kinds of pelts can trap fur. So this is from this paper over here, and this is an experiment that they did where they took samples of these furs and they put them in a chamber where that was pressurized to whatever depth these animals dive. And they showed which ones, these guys over here, maintain a layer of air, and these guys do not. Okay. So one of the questions you might ask is, why is it that some of these get that nice layer of air, and some of them do not? So under what conditions is air entrained during a dive? Okay. Okay. So good news. We have fur, so we have these hairy surfaces. So we can now dive them into different fluids and see what happens. So we do that. And here's a movie of the dive. So here's diving. There's one that's slower. Here's a faster one. And I'll stop this in a minute and tell you what you're looking at. So the dark area is air. And this area, this is water. So this means that the fluid has made it all the way to the, so okay, imagine this is the inside of the otter over here. This is otter. This is fluid out here. This is the hair. This is hair that's been fully saturated. The dark area is where there's been a layer of air that's been entrained through the dive. And by the layer of air is sometimes called a plastron. So this is where there's been a plastron. Okay. And you can see by changing sort of the thickness of the density of the hairs or the speed of the dive or the viscosity of the water, you can change how big that layer of air is. So that length there, that's the length at which the inside of your otter is staying dry. So that's where you have that nice insulating layer of air. Down here is where your otter is wet, so it no longer has that insulating layer of air. And so if you're an otter and you're trying to use this to stay warm, your objective is to say, well, I would like H dry to be longer than the length of my otter, L otter. Okay, that's the mathematical statement that we have to check. Okay, so I just need a dry layer that is going to be longer than the length of an otter, and then I've got my nice plastron, and then I can use that as an insulating layer. Okay, so again, we can do this calculation. This is a calculation that can be done. Oh, by the way, I'm going to tell this story, but then I'm going to come back to surface tension. I realize I took out my surface tension slide, but I'm going to put it back in. Okay. So we do many of these experiments. So you can do slower dives and fast dives and more hairy and less hairy surfaces, and you can see how much of an air layer you entrain. You find that the length of that dry region depends on sort of a bunch of things. Let me move myself a little bit out of the way here so you can see it. Oh, I can't. That's all right. So it depends on the hair geometry. Again, this is similar to what we saw with the bats. It depends, only this time it depends on the length. So it depends on the length of the hair and the spacing of the hair. It depends on the fluid properties, the density and viscosity, the gravity and the dive velocity. And again, if you are now an animal and you are and you're evolving different morphologies, I can't change gravity. I can't change the properties of the water I'm going into, but I can evolve that length and spacing of the hair, right? So that's the thing we're going to look at, again, just like with the bats, to see what is the length and spacing that you need in order to stay dry. And for those of you who prefer equations, this is the equation, right? So the dry layer depends on the ratio of the hair length to the spacing, or again, the spacing, and this is things like gravity and the fluid properties, the material properties of the fluid. Okay, so it turns out, so these numbers are all known, right? So we know, if an otter is diving from land, we know at what speed it's going to hit the water. It's just ballistic motion. We know the viscosity of fluid, we know the density of fluid, we know gravity. So this is just a number, and we can calculate what that number is, and we can ask, okay, what is the ratio of the hair length to the hair spacing that you need in order to stay dry for the length of an otter? Okay, so you do that. And you find that it is, roughly speaking, about 400. So you need that ratio of the length to the spacing to be bigger than 400. And so now I can put in the length and the spacing of all those seals that were measured in that biological paper, and check what is that ratio. Okay, and what you find is that this is a harp seal, so their ratio is about 52. So you expect them to be wet. Sea lion is 89. You expect them to be wet. Fur seal, okay, fur seal is the first one that beats it. So the fur seal you expect to be dry and keep a layer of air. And the winner of having the most longest, densest hair is the sea otter, coming in at 693. So they are going to be very, very dry. And I can now compare this to what I showed you before. This is what's actually measured in that paper. And so you can see these over here, these are the phosid seals. So, and I think that's a harp seal I have down there. So those guys are, we expect those, this guy, so I have pink goes with pink, so those should be wet. Sea lion orange goes with orange, that should be wet. Blue goes with blue, so those should be dry, and the otter's not even on this chart. So yeah. So this is, in fact, the fur seals and the otters perhaps have evolved this density so that they can rely on this layer of air rather than blubber to stay warm underwater. Okay, and I'm gonna put up the final slide, but I'm gonna say one thing on surface tension first, because somebody asked me about surface tension. So bear with me. I'm gonna see if I can unskip the slide. Hold on. Okay. Okay. Let's see. Do I do this? Oh, I might have to stop sharing. Okay. No, I'm going to show you the last slide, and then I'm going to go back and answer the question about surface tension. So the last slide is, of course, sorry, that's what we talked about before. That's just a nice picture of otters and bats and sperm. But the last slide is this one, which is the acknowledgements, because I have to acknowledge, of course, all of my students and postdocs and colleagues who've worked on this. And of course, the Selby Fellowship for giving this fantastic opportunity to come and travel around Australia. So I'm going to thank you there, and then you can ask me about surface tension. Thank you for good.